Friends, myself Priyanka Goswami. In this session, we will discuss about the chapter Laplace transformation, the subject electrical circuit and network. Now, Laplace transformation. Laplace transformation is a very powerful method for solving linear differential equations, as the transient response of an electrical circuit can be described by a linear differential equation. Hence, Laplace transformation finds its application in solving the transient behavior of the electric circuits. Now, there are certain steps. In the first step, the differential equation is transformed into an algebraic equation. This algebraic equation is then solved conventionally in the next step, and in the last step, the solution is transformed back in such a way that it becomes the required solution of the differential equations. Now, the Laplace transformation of a function f of t is defined as fs equals to L of ft equals to 0 to infinity ft into e to the power minus st dt, where s being the intermediate or transformed variable and s is the part of the exponential function, and it is described in equation 1 that to have Laplace transformation of f of t, the original time function f of t must be multiplied by e to the power minus st and then integrated from t equals to 0 to t equals to infinity. Also, f of t is to be defined for t greater than 0 and f t equals to 0 for t less than equals to 0. Now, inverse Laplace transform. Inverse Laplace transform permits going back in the reverse direction, that is from S domain to time domain. So the equation of inverse Laplace transform is L inverse f of s equals to f of t equals to L inverse L of ft, that is equals to f of t. Now Laplace transform of unit step function. The most common driving function in electrical engineering is the unit step function, and it is denoted as f of t equals to 0 when t less than equals to 0 and f of t equals to 1 when t greater than 0. That is, the function has no magnitude for the time t less than equals to 0 and has a positive unit magnitude at time t greater than 0. So Laplace transformation can be obtained as f of s equals to L of ft equals to 0 to infinity e to the power minus st dt. Therefore, f of s equals to 1 by s. The unit step function in electric circuit represent the closing of a switch applying a constant voltage V to the circuit. So, its Laplace transform would be V by S. Now, Laplace transform of exponential function. Exponential function being also very common in electric circuits, and it is described by f of t equals to e to the power minus alpha t. Now, direct application of Laplace transform method gives f of s equals to L of f t equals to 0 to infinity e to the power minus st into e to the power minus alpha t. Here we put f of t equals to e to the power minus alpha t, which is equals to 1 by s plus alpha. So here time t is kept restricted at the positive values. Now Laplace transformation of sinusoidal function. The function being extremely common for circuits encountering AC sources. The sinusoidal function in time domain is given by f of t equals to sin omega t, which is equals to 1 by 2j e to the power j omega t minus e to the power minus j omega t. Now fs equals to 1 by 2j 0 to infinity, integration 0 to infinity e to the power minus st plus j omega t minus e to the power minus st minus j omega t dt. Now fs equals to 1 by 2j e to the power minus s minus j omega into t by minus s minus j omega minus e to the power minus s plus j omega t by minus s plus j omega. Limit is 0 to infinity. Now fs equals to 1 by 2j 1 by s minus j omega minus 1 by s plus j omega. After solving, we get fs equals to omega by s square plus omega square. So ft equals to sine omega t and fs equals to, we can write omega by s square plus omega square. Now Laplace transform of cosinusoidal function. This function is given by f of t equals to cos omega t and cos omega t equals to 1 by omega ddt of sin omega t. The Laplace transformation of the cosine function is L of ft equals to L of cos omega t, which is equals to 1 by omega s into fs minus f of 0. So, L of cos omega t equals to 1 by omega s into omega by s square plus omega square minus 0. That is equals to s by s square plus omega square. So, when f of t equals to cos omega t, we can say f of s equals to L of cos omega t equals to s by s square plus omega square. Now, Laplace transform of ramp function. A ramp function is given by f of t equals to t. Now, directly apply the Laplace transform method. So, f of s equals to 0 to infinity t into e to the power minus st dt. Here we put f of t equals to small t. Now, integration by parts gives f of s equals to minus t into e to the power minus st by s integration 0 to infinity plus 0 to infinity 1 by s e to the power minus st dt. So, after solving, we can write f of s equals to 1 by s square. This is the Laplace transform of some useful functions. Now, Laplace transform properties. The main properties of Laplace transform can be summarized as linearity, first shifting theorem, and change of scale property. Now, linearity. Let C1 and C2 be the constant. So, ft, gt be the functions of time t. Then, L of C1 ft plus C2 gt equals to C1 L of ft plus C2 L of gt, because C1 and C2 be the constant. Now, first shifting theorem. If L of ft equals to fs, then L of e to the power at into f of t equals to f of s minus a. Now, change of scale property. If L of ft equals to fs, then L of f of at equals to 1 by a f of s by a. This is for frequency scaling. And L of f of t by a equals to a f of as. This is for time scaling. Now, initial value and final value theorem. If f of t and f of s is Laplace transform pair, so f of t, L and f of s, then initial value theorem is given by limit t tends to 0 positive, f of t equals to limit s tends to infinity, s of fs. So, that is equals to f of 0 plus. Now, proof. So, Laplace transform of a function f of t equals to 0 to infinity e to the power minus st f of t dt, which is equals to fs. Now, we apply Laplace transform of its derivative. Now, L of f dash t equals to 0 minus to infinity e to the power minus st f dash t dt. So, s fs minus f0 minus. Consider the integral first part. So, now 0 to infinity e to the power minus st f dash t dt. So, here we split into two integrals. First is 0 negative to 0 positive e to the power minus st f dash t dt plus integration 0 plus to infinity e to the power minus st f dash t dt. Now, after integrating f of t, limit is 0 minus to 0 plus 0 plus to infinity integration e to the power minus st f dash t dt. So equals to f of 0 plus minus f of 0 minus plus integration 0 plus to infinity e to the power minus st f dash t dt. Now substituting equation 2 in equation 1, f of 0 plus minus f of 0 minus plus integration 0 plus to infinity e to the power minus st f dash t dt equals to s into fs minus f of 0 minus. Now cancelling f of 0 minus on both sides. So integration 0 plus to infinity e to the power minus st f dash t dt plus f of 0 plus equals to s into fs. So we can write f of 0 plus equals to limit s tends to infinity s into fs. Now limit t tends to 0 plus f of t equals to limit s tends to infinity s into fs equals to f0 plus. Hence, initial value theorem is proved. Now final value theorem. If f of t and f dash t both are the Laplace transformable, so s into fs has no pole in z omega axis. So limit s tends to 0, s into fs equals to limit t tends to infinity f of t. Now from differentiation property of Laplace transformation, we can write integration 0 negative to infinity f dash t to the power minus st dt equals to s into fs minus f of 0 minus. So here limit 0 minus is taken to take care of the impulses present t equals to 0. So we take limit s tends to 0. If s tends to 0, then e to the power minus st equals tends to 1. So limit s tends to 0, integration 0 to infinity f dash t dt equals to limit s tends to 0, s into fs minus f of 0 minus. Now f of infinity into f of 0 minus equals to limit s tends to 0, s into fs minus f of 0 minus. Now f of infinity equals to limit s tends to 0, s into f of s. So final value theorem is proved. Thank you.